Okay, in this video we're going to be doing some examples on vectors. So what I first want to do is I want to give you a vector called v, and I'm going to give you the following components. So let's say it has 0, 1, and 2. Now the first thing I want to do is I'm going to plot this vector on a set of axes. So we're going to start with x on this side, y and z going up. So obviously the first coordinate is along the x-axis, so that's just going to be 0 here. Second coordinate is going to be 1 along the y-axis. And the third coordinate is 2 along the z-axis. So basically just combine all these points together, and that gives us the point in which we're going to go. So now all we need to do is we're going to draw a line that goes from the origin to that point here. So this point will essentially be 0, 1, 2. And this is the vector v. Now, what I want to do is, I want to find what the length of that vector is. And there is a very interesting connection that we already discussed that uses the distance formula. So we know that the distance formula gives us the distance between any 2 points. So if I have, for example, x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, and I can continue to expand this in the case that we were dealing with more than 3 dimensions, but that's not the case in here, so we're just going to limit ourselves to just 3 dimensions. So this is what the distance formula looks like, and we know that we take the square root of both sides. That's going to give us the total length from any point x1 to the point x2. Now, if we take the magnitude of a vector, we already defined this as the square root of the squared component. So what we do is we take the components and then we square them and add them together like this. So in essence, this is just going to be the square root of 1 squared, that's 1, plus 4. So that's square root of 5. So whatever units we're actually dealing with, that's just going to be square root of 5 units. And that's just what it is. Now, suppose we were interested in finding that distance using the distance formula, then all we will need to do is define 2 points. So this one would be 0, 0, 0. So that's the origin of these 3 axes. And the point P would be our endpoint. So if we were to use the distance formula, we would have the following. So the endpoint is going to be 0 minus 0. So basically that's just 0. Then we're going to have 1 minus 0. So 1 minus 0, that's just 1. And then we're going to have 2 minus 0. And all of this is going to give us the same. So in general, vectors are just a generalization of coordinates in any dimensions. And not only do they give us a magnitude, but they also give us a direction. And that's going to be very useful when we actually apply this to physical problems. But for now, let's just focus on some of the main properties that vectors have. Now, having discussed this, let's see if we can do some other very interesting things with this. So let me give you the following problem. I want you to find a unit vector, let's denote the unit vector u, that has a magnitude of 1. So it has a magnitude of 1, but I want it to point in exactly the same direction as v. So basically what I want you to do is I want you to create a vector u, which I'm drawing in blue here, and I want that vector to have a total length of 1, so that's going to be shorter than the length of v in this case, but it is also going to point in exactly the same direction. So how would we actually go about doing that? Well, we know that in some way the components of u should match the components of v. So there should be some proportions maintained here. So we know that you cannot have any components along the x direction, so it should just be 0. It has no projection along the x-axis. So what we can do is we can say that the first component is just going to be 0. Now the next component is going to be a projection here, but obviously we don't know what that is. Let's just for a second assume that this is 1, and let's assume that this is 2. Well, there is a problem. We know that if we take the magnitude of these components, we're just going to get the square root of 5. Now the question is, how do we actually make this expression here into this expression here? Well, it turns out that all we need to do to convert the square root of 5 into 1 is just divide by the square root of 5. So basically, if you take the magnitude divided by the magnitude, you get 1. And that sounds a little bit trivial, but how about I do this? How about I take this vector, and I tell you this is equal to the vector v over the magnitude of the vector v. Well, if we do that, we know that we're going to have 1 over the square root of 5, and then we're just going to have the components of v, so that's 0, 1, 2. And now what happens is that this is going to be multiplying each of these components individually. So if we were to calculate the magnitude of this vector now, so let's take the magnitude of u, then we're going to get the square root of 0 over square root of 5 squared plus 1 over the square root of 5 squared plus 2 over the square root of 5 squared. And what does that give us? Well, this is 0. This is going to be 1 over 5, so we're going to have square root of 1 over 5. Now here we're going to have 2 squared, that's 4. This squared becomes 5, so this is going to be 4 over 5. And as it turns out, this gives us a magnitude of 1. So in general, for any vector that points in the direction of a specific vector, all you need to do to convert it into a unit vector is divide the vector by its own magnitude. And this is a really useful thing that we need to know about, because we will be using it to define vectors and other physical quantities in later videos. Now, a final note on this is that generally we don't represent a unit vector with a different letter. So instead what we do is, if we want a unit vector that points in the direction of v, we use this little hat notation on the top. So basically we just define it as the vector over its own magnitude. So this is just a unit vector version of this. And this is a really useful thing that we will come across later on. Now, a few things that I might just tell you about. So I'm just going to give you a few examples of some things that you can do with vectors, which I find quite interesting. So the first of them is going to be vector addition. So the general thing about vector addition is that if two vectors have the same number of components, then in order to add them, you're going to create a new vector that is going to have the scalar components added together. So basically the first component of A plus the first component of B, then the second one of A plus the second one of B, and then so on and so on. So for n dimensions, whatever number of dimensions you're dealing with, you're going to have this. So if I give you two vectors, let's say A equals to 0, -1, 3, and then B is something like 1, 0, 1, then I can easily perform two operations. I can say A plus B is going to be equal to 0 plus 1, that's just 1, then -1 plus 0, that's -1 again, and then 3 plus 1, that's going to be 4. So that's the result of this vector. And if we do the opposite, if we take if we subtract the two vectors, then what we're going to get is the following. So we're going to have 0 minus 1, that's -1, -1 minus 0, so that's still -1, and then 3 minus 1, that's going to be 2. So those are two elementary operations that we can perform with vectors. Now, you might be thinking, can we actually do multiplication of vectors? And the short answer is no. If you were to multiply two vectors like this, so let's say A1, A2, and I'm just going to use the two-dimensional case just to illustrate what's happening. In general, you cannot perform this kind of operation because we haven't really defined how the multiplication is going to work. We don't know which elements we're actually multiplying by each other, and we don't know how we're going to deal with that. And this is something that we will discuss in the next video. Now, how about something like vector division? Can we actually do this? Well, the answer is we cannot. So in general, we are constrained to two operations with vectors, addition and subtraction. And in the next video, we're going to explore another very important operation between vectors, namely A and B. Now, before we move on to that one, I want to talk about a very, very important application of vector subtraction. So let me just get rid of this. So this is very straightforward. Addition and subtraction, you just add or subtract the elements together. So now let's suppose that we have a point, or rather 2 points in space. Let's say you have a point here, and then you have a point there, and then you have the origin here, right? And let's say I wanted to draw a vector that goes from point A to point B. And I'm going to give point A some coordinates. Let's say it has 2, 1, and then actually, for the purposes, let's make this 4, and let's make this something like 3. And then I'm going to give V some other coordinates. So let's say that's 0, 1, and then 5. Okay? So I want to find a vector that points from A to B. Now, there is a standard method to do this. So what I'm going to do is, instead of just trying to take a distance formula here, to use a distance formula to find the length and then so on, I'm going to do something very simple. I'm going to define two new vectors. So one is going to go from the origin to the point A, and another one is going to go from the origin to point B. I'm going to call this one vector A, and I'm going to call this one vector B. Now, a very quick way to create a vector out of a set of coordinates is saying the following. If your vector goes from the origin to the point, then all you do is you replace each coordinate by the element of the vector. So this vector would be 2, 4, 3. And then the vector B is just going to be 0, 1, 5. So this is a really quick way of doing that, and it's really useful. So if your vector is going from the origin to some arbitrary point in space, then the elements of that vector are going to be equal to the coordinates of the point it is going off to. Now, in order to obtain the vector that goes from A to B, all we need to do really is just subtract. So V in this case is going to be the endpoint, so basically vector B minus the starting point, which is given by vector A, so minus A. And then all we do now is we know that we just subtract, so we're going to have 0 minus 2, so that's going to be minus 2. Then 1 minus 4, that's minus 3. And then 5 minus 3, that's 2. So that's it. We just found a vector that goes from this point A to this point B, simply by defining two vectors from the origin pointing to the start and the end of the vector B, and then subtracting the components together. Now this is very important because we need to make sure the order corresponds to the where the vector is pointing. So if our starting point is A, then that's the vector we need to subtract from the other. Basically, we do endpoint minus starting point. If we were to use the opposite orientation, then you would notice that we would get the same thing, but we would get inverted signs. So all the signs would just get inverted, and what would actually happen is we would get a vector that goes from B to A instead. So technically this vector has the same magnitude, but it has a completely opposite direction to the other vector. So this is basically what we mean when we are defining a specific direction. We need to take care of how we perform the operation. And this is really useful because if we want to define positions in space, and this happens quite a lot when we deal with engineering and physics problems, we want to locate particles in space or bodies in space and see how they're moving with respect to other bodies, we need to use this kind of definition. And in the next video, we're going to introduce a very important concept that is called the dot product of two vectors.